Okay, let's go to the next topic. The next topic is the general mass. We are dealing with the general mass when we have objects, right, or system of objects, and we want to take only the mass, right, in one point. And we call that point the general mass. It's easier to work with one point than with many points, many masses, right, when we're dealing with motion, especially. Okay, let's do it. For example, imagine that you have a big object, right? How we can find the center mass of that object? That's this is case, right? Well, at the center, right? Different object, correct? Another object, well, at the center by symmetry. Now, what happens if we have these two objects? We're looking for the center mass, right, of these two objects. Now, to study that situation, we use the concept of the lever, right? The concept of equilibrium, right? Imagine that we have these two objects, right? Right now we find the equilibrium position to be that one, right? Actually, that equilibrium position is the center mass of these two objects. We will label this M1, right, and M2, and the center mass, right, of these two objects at their centers, right, and also the distance from the equilibrium position to each of the center mass, like L1 right here, M2 right here. So the condition for equilibrium for this system, right, is gonna be M1 L1 equals to M2 L2. Okay, let's apply these conditions when we have, right, two objects, like in this case or like in that case, right? The principle is the same. Let's do it. Imagine one more time we have this object right here and this object right here. And let's connect, right, the central masses similarly to this one, right, by a line, right, imaginary line. Now we call that X, the X direction. Now, because we're dealing with position, we're looking for the position, right, of the central mass, we need an observer. Remember, position is relative, depends on the observer. Okay, imagine that the observer is right here. And now, one more time, this is M1, right? This is M2, correct? And the distance from the observer to M1 is X1, right? From the observer to the central mass, XCM, central mass in the X position, right? And from the observer, right, to the second object, X2. Okay, now let's use this condition to find, right, an equation that is represented by this observer. Okay, let's do it. One more time, we label this as L1, right, and that was L2. And we go back to the first condition. So what do we have? M1 times L1, but L1 is this distance minus this distance, right? This minus this is equals to L1. So now we write XCM, right, minus X1 equals to M2 times L2. But L2 is this distance minus this distance, correct? Okay, so now we X2 minus XCM, right? Right. Now, because we're looking for the central mass, right? Looking for that quantity, right? Let's start for that quantity. Perfect. So what do we have right here? M1x, right? Cm minus M1 x1 is equals to M2, right? X2 minus M2x Cm, right? Perfect. Let's arrange it again. And what do we have? We have that this quantity times M1, right, plus M2 must be equals to, look, this term is negative, it goes positive to the side, right, M1 x1 plus M2 x2, correct? From here we solve for this position, right, of the central mass in the x direction equals to this sum, right, x1 plus M2 x2 divided by, right, the total mass. Correct? In general, if we have, let's say, 3 or more objects, how we can simplify this equation in this way. In general, we can write this in this way. This equals to the sum, right, of this product divided by this sum, right? This is the equation for discrete particles, right? That give us the position of the center of mass in the x direction. The same thing in the y direction, right? In the y direction, we have the same formula. This is the product, the sum of this product, right? Now gonna be y, right? And again, the total mass, correct? Also, we can do the same thing for the position vector, right? Using the position vector, position, right, vector. Remember, position vector is r, generally 2D. Let's work in 2D to make it easier, right? So what do we have then? That this position vector, right, the center mass of the position vector, right, is equals to, well, by definition, right, it goes x, right, plus y, j hat, correct? Perfect. So we have then the position vector. Also, we can use position vector using this notation, right? They have the subform, as you can see right here. So that forms give us then this center mass of position vector, right? Or position vector of the center of mass, right? Equals to the sum, right, of this product divided by the total mass. They have the same form, right? So these are general form for the center mass, correct? When we have discrete object. Now, what happens if we have a continuous object? We have a solid. When we have a solid, right, the equation takes this form, right? The equation for the position, right, of the center of mass equals to 1 over the total mass times the integral, right, times the integral of r sub I dm. This is for solid, right? Solid. Okay, now we found the position vector of the center of mass. Now let's go to the velocity of the center of mass. How we can work with that velocity? Okay, let's do it. So how do we define velocity? Well, remember it's distance divided, well, that's the speed, right? Distance divided by time, or velocity displacement divided by time, right? Let's do it. So what do we have then? The velocity of the center of mass is equals to, okay, this derivative, right, respect to time. Okay, but what is this? Well, this is just this one right here, correct? Okay, let's do it. So it's equals to the sum m sub I, right, d, right, the derivative for each position, right, respect to time, correct? Correct, but we need to divide it by the total mass, right? 1 over the total mass. Perfect. Then this is equals to what? This is equals to 1 over the total mass times, what should be this part? Okay, times the sum of m sub I, right? dr over dt is the velocity, right? It's gonna be v sub I. Correct? Perfect. And then what do we have? This is equals to, let's arrange it in this way, right? We multiply by the total mass, mass times the velocity of center of mass is equals to, well, we're doing this with vectors, okay? So equals to what? Equals to the sum, right, of this product. But what is this product, right? We already found it before, right? Momentum is defined as mass times velocity, right? So if we apply this value right here, so this equals to what? The sum, right, of this momentum for each particle, right? Now, but what is the sum or the momentum, right? It's gonna be the total momentum. So this is actually the total momentum, right? So the total momentum then is equals to, the total momentum is equals to the total mass, the mass of the total system, right? times the velocity of the central mass of the whole system, correct? So this is a very important conclusion, right? Instead of working with particles individually, we work only with the velocity of the central mass times, right, the mass of the total of the particles. So simplifies a lot this equation when we have a system of particles and we're looking for or dealing with momentum, correct? Perfect. Now what happens if we work with acceleration? We found first position, velocity, now let's go to acceleration. Let's see how it works. Okay, the same thing as for velocity, right? Acceleration of the central mass is equals to, right, this velocity of central mass with respect to time, correct? But how do we define then this velocity, right, of the central mass? We found it, right? Let's jump to this step right here, correct? So it's equals to what? 1 over mass, the total mass, times the sum m sub I, v sub I, right? Because it's derivative right here, right? The derivative, right, respect to time right here, correct? Perfect. But what is this now? Now that's the acceleration of each individual particle, right? So it's equals to what? 1 over m times the sum m sub I, a sub I, correct? The acceleration for each particle. Okay, the acceleration for the sub I particle, or the ith particle. Okay, perfect. Great. Now let's do the same thing as for velocity, right? Let's multiply by the total mass, and what do we have? Mass times the acceleration of the central mass is equals to, right, this sum, right? But what is this product? Mass times acceleration is force, right? So it's equals to, right, the sum of the individual forces. But what is the sum of the forces, right? Is the net force, correct? So it's found then that the net force, right, Newton's second law, remember Newton's second law, right? The net force, right, now is equals to the total mass times the acceleration of the central mass, right? Instead of taking the acceleration of the particles, let's take the acceleration of the central mass times the total mass, give us the net force, right, acting on a system, correct? So these conclusions are very, very important, right? These two, the net force and then the momentum. Also, right, velocity of the central mass, right? Those are very important formulas, correct? Okay, and we have, for example, object like this one, right, that give us how it works, right? The central mass, right, is concentrated at that point, so doesn't matter you move this object right around, stay the same. Also, you can use, right, using your finger, right, correct, like that. Oh, you want, right, like your pen right here, right, using like this, but it works, correct. Well, with this we finish this introduction of the central mass. Remember, right here we're dealing only with the formulas with the theory. Later in the lecture, in the class, we are solving problems, right, to apply, right, these formulas, this concept. Okay, thank you.